Vacuum Fluorescent Displays. Surely one of the greatest display technologies ever created. Invented in 1959 by Philips, they've been popular all the way up even into the 90s, and you can even still buy modern electronics using vacuum fluorescent displays. And yes, they are reasonably easy. I say reasonably easy because of the voltages involved to run from an Arduino. The principle of operation of a vacuum fluorescent display is the same as a triode valve, which again is similar to a cathode ray tube, which of course is what old televisions used to run on. Now, cathode ray tubes run on hundreds and thousands, even tens of thousands of volts. Vacuum fluorescent displays thankfully don't, but they do still run on slightly more than the 5 volts that an Arduino can provide. This one is currently running at 15 volts, and I've actually turned it down so that it's more visible. To the naked eye it's quite dim, on the camera it looks quite bright. If I turn it up to the voltage that it's supposed to be running at, so that you get a good bright display, it swamps out on the camera. But to the human eye that looks nice and bright now, but that is running at 31 volts. So how does a vacuum fluorescent display actually work, and how do you interface it to an Arduino? Well, let's disconnect this and get the pad out and I shall show you. Basically, a vacuum fluorescent display is a glass envelope with a vacuum, all the air taken out. Within there you have a filament. This is looking on end view, by the way. Let's bring this in so it's like so. You have a grid and you have phosphor coated anodes. The idea is you heat up the filament which is the cathode in this case. It's coated with special chemicals which, when heated up, emit electrons. Let's have some red electrons coming out from here. This emits electrons in all directions. So you pass a current through the filament, electrons are emitted. The grid, which is a mesh of very, very fine wires, acts like a transistor. It will either pass those electrons through or it'll push them away. If the grid is at the same potential as the filament or the cathode, these electrons will be repelled because like charges repel. Actually, I'll put these repelling ones in blue. You can see them. So those electrons are being pushed away. That's better. Like so. At the same time, the anodes here are also at the same potential as the grid. So all those electrons are pushed away. when an anode and the grid, it's important that both of them, are at a higher potential than the cathode, the opposite happens. Let's draw another clean picture, shall we, for that one? So here is our glass bubble, there's our filament, our grid, our two anodes. Okay, so if we have a voltage here, let's say we have 5 volts on the cathode, and we want the electrons which are spewing out of here to get to the anodes, the potential on the anodes needs to be higher than the potential on the cathode so that it attracts the electrons. So if you think the voltage of the electrons is 5 volts and that's effectively negative, you need to have a positive for those electrons to be attracted to. So if we have that as positive relative to 5 volts and the grid positive relative to 5 volts, the electrons coming from here are attracted to the grid at very high velocity. We're talking speed of light here. And the grid being very, very, very fine wires doesn't just soak up all the electrons. Most of them just go straight through to that positively charged anode. This one here, for instance, is negative, or at the same potential or below the potential of the cathode. So these ones, although they're attracted by the grid, are pushed away by that anode. Okay. So if we look at the top view of the display, each segment of the digits within it is one of the anodes. You see these white spots underneath? Those are the connections to the grids, which form an off rectangle in this. It's more like a squashed pentagon, I think. On this specific display, it can be any shape, it just happens to be a squashed pentagon in this case. And then running all the way across the front of that is the filament. You can't see it easily with the naked eye because it is so fine. So let's zoom in into the elements so you can see the grid. You can see the outline of the grid around the individual digit. And within that grid, it is a very, very fine wires. In fact, if we zoom in to and focus on just the grid, there we go. You can see how fine those wires are. The filament is actually running across that display, but again, you can't see it. You can only really see it once it's warmed up. So there we go. We now can see the orange filament with the glowing phosphors behind it. So how do we actually display something on here using an Arduino? Well, that's when voltages start to get tricky. Let's go back to the pad again. and a top view. What we have, there goes my pen lid, is a set of digits. Let's just have 4 in this case. Across each one is a grid. And then across the whole thing is the filament. So we need to have a voltage across here and apply voltages. I'll also add a couple of, these are all multiplexed. Those are anodes. So we've got grid, anode, anode, cathode, cathode, grid, grid, grid. So we have a voltage applied across here. Let's call that plus 5 volts and 0 volts. Then we apply voltages to the segments and grids that we want to turn on. Now those voltages have to be higher than the high end of the filament, 5 volts. The actual voltage you need it to be higher is dependent on how many segments you've got, how fast you're doing the multiplexing, etc. Basically, the longer a digit is being displayed for, the brighter it will be. These specific displays have got 9 digits, so each digit is only being displayed for a 1/9 of the time. So you effectively get a 1/9 of the brightness. So for full brightness on this one, I was using 31 volts. So we apply 31 volts to an anode and a grid. 31 volts just happens to be the maximum that my power supply will provide. So the voltage difference between the 5 volts and the 31 volts, of course, is 26 volts. So between here and here is 26 volts. But that poses a small problem, because between here and the grid is 31 volts, because here the voltage is 0 volts. Between those 2 points there. So you're going to get a brighter digit this end than you are at this end, because of the greater voltage difference. And that poses a problem. So what do we do? The simple option is swap those over. But now the dim digit is this end and the bright one at this end. So you've effectively swapped them over. If you keep doing that very rapidly, the dim digit will keep swapping which end it's on, and you shouldn't see any dim. If we look at it as a little graph, we have the how's best to depict this? The digit number effectively that way, and the voltage of the cathode at that point. Starting with 5 volts there, and digit 1 is 31 volts, because here the voltage is 0 volts. Between those 2 points there. So you're going to get a brighter digit this end than you are at this end, because of the greater voltage difference. and that poses a problem. So what do? The simple option is swap those over, but now the dim digit is this end and the bright one at this end. So you've effectively swapped them over. If you keep doing that very rapidly, the dim digit will keep swapping which end it's on, and you shouldn't see any dim. If we look at it as a little graph, we have the how's best to depict this? The digit number effectively that way, and the voltage of the cathode at that point. Starting with 5 volts there, and digit 1 there, we have a good straight line. Swap it over and we have 0 volts here going up to here. In the very centre there is a point where the brightness never changes, and you'd think that would actually be the dimmest point because you've got the extra 5 volt difference either side, but that's only partially there. Half the time it's a less voltage difference, but here the voltage difference is always the same. So the effect is actually that is the brightest point, and what you get is a slight brighter point in the centre. That's not voltage, that's brightness. That can actually be seen on the display that I've been showing you here. Not easily on the camera, but it can be seen by the naked eye. Let's bring this back in again and see, just out of interest, if I can get it to show that brightness difference. I zoom in to the display, can I see anything? If I turn the lights out on the bench, no. However, you can just about see the filament there, but it's hard to distinguish. However, if I were to just temporarily change the circuit so that it only has a static 5 volts, see if we can see that better. There we go. You can see the digits on the left are still illuminated, which is the ground connection. The digits on the right have faded out completely. Put the circuit back how it was. And all the digits are about the same brightness. Now, normally the filament of the vacuum fluorescent tube is powered using a transformer and an AC current rather than DC. But we don't have that on an Arduino, but we do have PWM, and we do have the ability to change pins being high or low. In this specific example, I've decided to just use switching of pins high and low. The filament, interestingly, takes about 17-18 milliamps, so it's safe to connect it directly across two pins. You do, however, need to be able to switch the higher voltages. And to do that on this circuit, I've, to keep things simple, used the ULN 2003 Darlington transistor pair drivers. They're very common, very easy to get hold of. And the driver circuit for both the gate, the grid, I do wish I wouldn't keep calling them gates, they're grids, and the anodes is identical. And it's simply the signal coming in from the Arduino goes into the Darlington pair buffer, which is open collector, a pull-up resistor, and into the gate or grid, not gate, or anode. So to expand that out a little, you have basically the base going into one NPN transistor, into another NPN transistor, and down to ground. That's the pull-up resistor there, and that's your outgoing signal. I chose these purely because they're in a convenient chip form. You could just as easily use any small signal transistor which can cope with the voltages, in which case it's just simply into the base, emitter goes to ground, your signal with a pull-up resistor. For this display, because it's 8 segments with 9 digits, that's 17 transistors needed. That's why I chose to use the ULN 2003, because it's just 3 chips rather than 17 transistors. I shall of course post the full schematic of this and the code on my blog site. We'll have a link to it in the description below. Let's wire it up again, get it going. But I'll just give you a quick overview of the circuit. Basically, we have the Arduino with nodes here, cathode, grids here, identical to driving an LED multiplex display. You drive each grid in turn and display the digit that wants to be on that digit. Because of the inverting nature of the ULN 2003s, the grids and the anodes are active low, so you have them all high except the one that you want to drive at the time, which then allows the excuse me, allows the pull-up resistor to do its job and pull that gate, that grid, up to 31 volts. Similarly with the anodes, you pull the input low to allow the output to switch off, so the pull-up resistor can pull the anode up to 31 volts. There's not a huge amount else to tell you about the circuit. These two wires here go to the filament, which on this display is either end, and those are just alternating one on, one off, and switching backwards and forwards at the same speed that the display is refreshing. And that's really all there is to tell you about it.